we're going to break it into two sections to talk about. So each section will be shorter. First, we're going to talk about, introduce you to the integral test. So we're going to discover this together. So what do we have here? Remember, we have these two functions. Both of them are in a shape like this at the first quadrant, and it's going to go down like this, closer and closer to this x-axis as x goes to infinity. However, if we consider the area under the curve from 1 to infinity, see this green shaded area over here? This one here, actually the area here is a finite area. It is equal to 1. We did that before. Even though this strip here is continued forever, okay? So, but this one over here, the area under this curve from 1 to infinity is actually infinity. And at that time, we investigate why this one here has the finite area under the curve from 1 to infinity, and this one doesn't have a finite area. So we investigate this kind of p-integral because the area under the curve from 1 to infinity corresponds to this integral over here. So we want to see what happens to the p. What kind of p over here? It's going to converge. So, and at that time we do the investigation on this kind of p-integral, we know the conclusion is this p-integral converge even only if p satisfies what condition? You guys remember? Greater than 1. Yes, greater than 1. Okay, thank you. So when p is greater than 1, it converges. Okay. So for example, over here, the p here is 2. Okay, and that integral corresponds to the area under the curve from 1 to infinity is a finite number. It converges to a finite number. In this case, equal to 1. But then here, the p is equal to the exponent on the x in the denominator here is 1. P equal to 1, which is not strictly greater than 1. And that integral over here corresponds to this area, the area under the curve from 1 to infinity, actually diverges. It diverges to infinity. Maybe for some more example, what about this one? If I have 1 over x to the 1.0001 here dx, x goes from 1 to infinity, this p-integral over here, convergent or divergent? It converges because the p here is greater than 1, right? Okay, good. So this one here converge, okay, because this is greater than 1, okay? All right, now let's investigate the corresponding series. So we have this p-integral. I'm going to find the corresponding series. So the corresponding series is this one, 1 over x squared. The corresponding series is 1 over n squared. So the x here is being replaced by n. And if you want to get a feel of how this series look like, you substitute. Okay, I forgot the infinity over here. Okay. We're going to substitute n here. Start from the first index and then keep on adding 1 to the index, right? Okay. So it'll be 1 over 1 square plus 1 over 2 square plus 1 over 3 square, etc. Right? Okay. So this is how this series here look like. Okay, 1 over n squared. Okay, n start from 1. Okay, and then to 2, and then 3 and 4, and then to infinity. So this series here is actually related to this 1 over x squared. Okay. So the relating function of this series here is 1 over x squared. We place the n here by x. And we know the graph of this, right? Which is this one, the same one we have. Okay, so we graph it. Now we're going to let the x value to be 1 and 2 and 3 and 4. So we have 1, right? 1 here, 2, 3, and 4, and 5, etc. So the function value is going to, at 1, is going to be 1 over 1 square, which is the y coordinate at this point, right? And then the function value when x equal to 2 is going to be 1 over 2 squared, etc. Right? Okay, you get the idea. So this is this and this. Okay. Now we're going to construct this rectangle using this as okay, and using this as the width, and construct rectangle. So that goes all the rectangle over here and here. I'm going to ask you, what's the area for this first rectangle? What's the area for this first rectangle? It's, oh, this is the one. One. It's a one. Yeah, it's the one. Because it's a one. Remember, this is 2, this is 3, this is 4, and this is 5, right? So it's going to be the height multiplied with the width, right? To get this area of this rectangle. So what is the height? The height of this is 1 over 1 square, right? Okay, and then what about the width? It's 1. All of them with equal to 1. So basically, the area of this rectangle is 1 over 1 square, right? Okay, so you agree with that? Okay. All right. What about this second rectangle here with this height and this width? What's the area of this rectangle? 1 over 2 square? Yeah, you got it. Good job. Okay. 1 over 2 square, right? Okay. And then the next one, everyone tell me the next one, 1 over 3 square, etc. Right? You continue like this. Okay. So now you're looking at this, you see this, those sum of those rectangle, right? It sum up to this. Looking at this, does it look like is the series over here? Isn't that is a sum? Yeah, it's a sum here. So this series here corresponds to those sum of those rectangle, right? The area of those rectangle, right? Now I'm going to separate it this way. So I'm going to draw a line here at 1 and x equal 1. I'm going to leave out this first rectangle and only think about some of the rest of those rectangles. Comparing the sum of those rectangles with area under the curve from 1 on, which one's bigger? We leave out the first one. Okay, only consider the second one on. So the sum of those orange rectangles comparing to the area under the curve from 1 on, which one's bigger? Yeah, the area under the curve is bigger, right? Because we have this space over here, right? So we know that it's going to be less than the area under the curve from 1 on. Okay, so we agree with that. Yeah. Yes, it's a less than sign. Now, what is this area under the curve? What's the area under the curve from 1 to infinity? The area under this curve of this function from 1 to infinity, can you express that using an integral? Yes, of course. Integral of what? 1 to infinity, right? It's the integral of the function 1 to infinity, right? Because we start from 1 over here and then to infinity. What's the function? 1 over x squared. The blue here, this graph over here is the graph of this function, 1 over x squared. So 1 over x squared dx, right? Okay. What do you know about this integral? What do you know about this integral? It converges, right? We actually know how, what it converges to. What does it convert to? Convert to 1, right? The area under the curve, we did that before, it equal to 1, right? It convert to 1, okay? So we know that. Now, based on this result, okay, based on this result, then we know this part over here is going to be less than 1 because this part here is less than the area under the curve and area under the curve is 1. So this part here less than 1. Now we're going to put the first thing here back, okay? So the first thing here is what? 1. In this class, always 1 or 0, okay? 1, okay? All right, so 1, and then this is less than 1. So the whole thing is less than what? It's less than. Okay, so this is 1, and this is less than 1. So the whole thing is less than 1 plus 1, which is 2. Okay, so that's less than 2. Okay, all right. So 1 plus 1 here is 2. So it's less than 2. So this series over here is going to be less than 2. We know that this series here, the sum is less than 2. So if that is less than 2, so we have this series 1 over n squared. We know that this series here is less than 2. So to see if this series converge or not, let's look at the n partial sum. If the n partial sum converge, then the series is going to converge. Now let's look at S1. S1 is equal to 1 over 1 squared. This is S2. And Sn is 1 over 1 squared, adding all the way to 1 over n squared. As you can see that as n increase, Sn increase. So Sn is increasing. The more chain you add to this, the bigger the sum here. So the n partial sum is increasing. So Sn is increasing, and it is also bounded above by 2. It's not going to go beyond 2. By the monotonic sequence theorem, Sn converges, and it's going to converge to a finite number less than this number 2. The monotonic sequence theorem that we talked about, it was in section 11.1. It says every bounded monotonic sequence is convergent. At that time, we break it into 2 cases. The first case is when the sequence is increasing and bounded above, then it converges. So if I have an increasing sequence and it is bounded above, then the sequence has to converge. So this is exactly what we have here. You see Sn is increasing and is bounded above by 2. So Sn had to go to a finite number less than 2. So this is the monotonic sequence theorem. The second case of the monotonic sequence theorem is when the sequence is decreasing and bounded below, then the sequence has to converge. Now, we have this Sn converge to a finite number less than 2. That means this series here is going to converge to a finite number less than 2. It doesn't converge to 2. If sum all this up, I think I remember it was pi squared over 6. So pi squared over 6 is about 9 over 6. So it's less than 2, okay? But, okay, so if you sum all this up, it should be a number that is less than 2. Okay, so it converges. Okay, so this series over here converge. So it converges. And now we have this observation. What do we know about this P integral here? This P series here converges, right? Because P equal to 2 greater than 1. And so using this method that we have just done, we can relate this series here with this integral and to conclude that this series over here converge. This one here imply this one here converge, then this one converge. Okay, and vice versa actually. Okay. Do you see the relation? Okay. See this one here, the P is equal to 2. This is actually P equal to 2. This is actually, what do we give a name here? This one here is called a P integral, right? This is called P integrals. And what do you call this? P series. Okay, this is called P series. So when this P integral here converge, then this P series here is going to converge. Okay, 1 over x squared here, 1 over n squared here, n go from 1 to infinity. Okay, so this is one of the observation for that. Okay, all right. Yeah.
Why is it less than 2?
Which one? Less than 2. Oh, why is it less than 2, right? So here it is 1, right? So we have 1 over here. Let's do this. So, okay, so this part here is 1, right? It's 1. And then what about the other part right here? The rest over here, what do we know about this? We know that it is less than 1, right? It's less than the area under the curve. So this part over here is less than 1. So this part over here, the green part here I highlighted, correspond to, what does it correspond to? It corresponds to this sum of all those rectangles right there. Do you see the relation? Okay. And they are under the curve, right? They're under this curve. So when you sum up all those rectangles, then the area, all those, it's going to be less than the area under the curve. The area under the curve, we calculated, and it was equal to 1 before. That was the result when we did the P integral. Okay, so this is less than 1. I'm going to move it here. So it is less than 1. Okay, therefore, the whole thing over here is less than 1 plus 1. So it is less than 2. Okay, so it's less than 2. This series here doesn't converge to 2. But we know the result is a finite number that's less than 2. In fact, it is pi squared over 6. Okay, like that. But so if you can show that this series over here is, the more term you get, the more it increase, but it is less than a finite number, then this series here is going to converge. It doesn't converge to this number, it converges to a number less than this. Okay. So now we can actually generalize this. If the P here is greater than 1, okay, we can actually use a similar method to prove that the series over here is going to converge when P is greater than 1. Yes, you got it. Well, so when P is greater than 1, and then this P series here is going to converge. All right. Now the next one, let's look at this. Let's look at this series here. 1 over square root of n. If I write it out the twin, it's going to look like this. The relating function is 1 over square root of x, and it's going to look like this. And p here is equal to, what's p? P equal to what? 1/2, which is less than 1, right? This integral here converge or diverge? Diverges, right? Diverges. It only converges when p is greater than 1, right? So this one here diverges. Okay, this P integral diverge. And this P integral here corresponds to the area under the curve from 1 to infinity. Okay. The area under the blue curve. Okay. So this is the graph, and then x go from 1 to infinity. So here's 1 and then to infinity. So that corresponds to the area under the blue curve from 1 to infinity. Now we're going to, again, we're going to find those corresponding function value at 1, 2, and 3, and 4, etc. So as 1 here, 2 here, 3, and 4, those are the function value. So the y coordinate at this point is 1 over square root 1. The y coordinate this is 1 over square root 2, etc. Now I'm going to ask you the area of all those, the sum of all those rectangles. Okay, let's look at the area for the first one here. What is this area? 1 over square root 1 multiplied with what? The width of this rectangle is what? 1. Yeah, all of them have width to be 1, right? And then the height here is 1 over square root of 1. So the area here is what? Yes, it is 1. Okay. Actually, it's right. Actually, right here. 1 over square root of 1, if I want to relate to this, okay? So it is 1 over, what's a long way from there to this page, okay? So 1 over square root of 1, okay? What's the area for the second rectangle? Yes, 1 over square root of 2 times 1, which is just 1 over square root of 2, right? Okay, and then you can keep going. Yes, the next one, 1 over square root of 3, etc. Okay, I'm going to put the arrow here so you can see. If I sum up all those rectangles, okay, comparing the area of the sum of those rectangles with the area under the curve, which one is bigger from 1 to infinity from here on? The one above the curve, which is, which one? Is the, yeah, those sum of those rectangles, right? So each rectangle here is going to be a little bit above, right? It's going to have a little bit above the curve. So when you sum up all those rectangles, Secondly, the sum of this is going to be more than the area under the curve because each one of them you have some extra above, right? So we conclude that that is going to be greater than the area under the curve, greater than the area under the blue curve from 1 to infinity. Well, what's the area under this blue curve from 1 to infinity in integral? Okay, it is an integral. It's the integral. Is it this integral? Yes, right? When you try to find area under the curve, then you will integrate the function and then you put x go from what to what, right? So this function here is 1 over x to the 1/2. And then the area under the curve from 1 to infinity. So integrate here, x go from 1 to infinity. So this one here corresponds to the area under the blue curve, okay? We know that it diverges to infinity. Actually diverges to infinity because this is a p integral and with p not greater than 1, right? So diverge to infinity. So we know that is diverge to infinity. Now this one here is actually greater than that, greater than that. So what do you think? This one here, the sum of those rectangle is going to greater than the area under the curve. So is it going to converge or is it going to diverge? Diverge and diverge to what? Infinity. Yes, very, very good. Okay, so it diverge to infinity. Yes. Over the curve. Oh, why this rectangle over the curve? Because this function here, good question. This function over here is the decreasing function, right? So you see that 1 over, this is 1 over square root of x. The bigger the x get at the first quadrant, then the bigger the denominator. Then, so as x here getting bigger, what happened to the function value? It gets smaller, okay? So as x get bigger, it gets smaller. So this is a decreasing function. So it goes down like this, okay? It's kind of like the airplane. It dipped to the ground, okay? And then now when you construct those rectangle, you take the left endpoint like over here. The function value at this left endpoint here is, well, you substitute 1 into the x. So you get 1 over square root of 1. So this is the y coordinate, this one, right? And because it's decreasing, the left-hand point is always the highest point in the interval because all of this is going to be less than that, right? So when you take the left-hand point, this rectangle is going to be above the blue, above the area under the curve right here, right? So the key information here is the function here is actually a decreasing function. So that's why here is above. If it's increasing function, this is not going to work, okay? So this type of function, 1 over x to the p, 1 over x to the p, this type of function is actually a decreasing function, okay? So it's important to actually pay attention to that. So that's a very good question. So when it's a decreasing function, and when you construct a rectangle using left endpoint, the rectangle is going to be above the curve. So the area is going to be greater than the area under the curve. So that's a good question. Yeah. Oh, not necessarily the series has to be monotonic like that. The trend is going to be decreasing or increasing. Sometimes it go up and down. Okay. For example, if the series here involves sine, say instead of n, maybe sine of n. So it go up and down, up and down. Okay. So this one, but this type, 1 over x to p, it has to be decreasing, right? The bigger the x, the bigger the denominator, the smaller the result, right? So it has to be decreasing. So from this, you know that the sum of those rectangle is going to be greater than the area under the curve. And we know the area under the curve here is divergent, it diverges to infinity, and this one here greater than this, that diverge to infinity, it has to be divergent and also diverge to infinity. Okay, so that's a good question. Now we write down the observation that we have. So this series over here diverges, actually diverge to infinity. Okay, doing the comparison, we know that what happened to this P series over here, it also diverges. Okay, so it also diverges. Now we put the observation, okay, and actually we can prove it by similar method. We have this important result here, and I put the star here, say, want you to remember. So when this P-integral here converge, okay, and when would this P-integral here converge? Converge if and only if P is greater than 1, right? Then the relating series, and that's called P series, is going to, this is also converge even only if P is greater than 1. So you can try to put them together and remember them together. Now let's try some examples, see if you understand what I'm talking about. Let's look at this series over here. Is this a P series? Yes. P is 1.001. Converge or diverge? Okay, good. Okay, no one said, everyone got this right. That's good. Converge. Okay, sometimes I use CONV for converge. Okay. Okay, and what about the next one? Diverge. Okay, because 1 over pi is about, it's about 1/3, right? Which is less than 1, right? Okay, then last one, converge or diverge? It diverges. Yeah, it diverges. You got it right. And this is actually, I think that kind of confuse you is this is actually accurate to write 1 over n to the negative 1, because this one here is simplified. It should be what? It's just n, right? So what is this series n? Right? N is just what? 1 plus 2 plus 3, etc. Right? Certainly it diverge to infinity, right? Yeah. So that's good. Okay, I'm glad that you guys are actually thinking, not just listen and not thinking. Okay, that's great. Now the next one, now we're going to talk about the integral test. You can make some very good observation. So for the integral test to work, we have a series, and then we look at the relating function. How do you get the relating function? You replace the n over here by x, then you get the relating function. Okay. If the relating function satisfies 3 conditions, so what are the 3 conditions? So it is, number 1, has to be continuous. What does it mean continuous? It means the graph has no break. Okay, it has no break. It's not broken. Okay. Number 2, it is positive. Okay, so for example, try to look at this one. So from 1 to infinity, this graph here has no break. It's continuous. Number 2, it is positive, which means it is above this x-axis, above or touching the x-axis. Never, it's not going to be negative. Okay, so it's not going to go below this x-axis. Okay, positive. Number 3 is just decreasing. So I think we keep bringing up the important for the function to be decreasing in order for it to work. Okay, so the function here is decreasing. In general, it goes down like this. Okay, on 1 to infinity, because we only care about from 1 to infinity, because the index of the series ends start from 1, right? You're not going to start from a negative index, so we only care from 1 to infinity. If this function satisfies these 3 conditions, then what happens here is, if that integral from 1 to infinity here converge, then the series here converge. If that integral here diverge, then this series here diverge. Do you guys got it? The proof of this is actually very similar to the proof we just did. Okay, we construct this rectangle sometimes under the curve, sometimes over the curve, depends on using the left or right endpoint. So I put a star here, and that's the one that you want to remember. This is a key idea for today, the integral test. So, okay, so without looking at this, I'm going to test you guys the three conditions, three hypotheses for the function. Okay, number one, the function f had to be what? Continuous. Number two, positive. And number three, decreasing. Yeah, on 1 to infinity. Okay, good job. Okay. Okay, now I'm going to modify this a little bit. So take a look at the function over here. Okay, suppose the relating function is like this. It's going to decrease after some index on, but before some index, it might not be decreasing. So it might go up, but after that, it go down. So this answers the question that Ryan asked, right? Is the series always like the trend is going to be decreasing? No, sometimes it go up first and then it go down. So the trend can increase first and then decrease after, like that. Can we still use the integral test for a function, the relating function that is decreasing ultimately? Okay, what does it mean decreasing ultimately mean?
That means from some index on, the function is always decreasing. So after the index m, the function is always decreasing. Then we say the function is decreasing ultimately.
What happened here is, can we still use the integral test to conclude that if the integral here converge, then this one converge. If this integral here diverge, then this one diverge. What do you think? Can we still apply the thing? Yes, good guess. Okay, yes. What's the reason? The reason over here is this.
We can consider the series, the index start from m. Since the function is going to be decreasing after m, we can apply the integral test on this series, the index start from m. If the function satisfies the three conditions of the integral test. In our last section, we talk about a series converges if and only if any of its tails converges. So the tail over here, when the index start from m, if it converge, then the whole series converge. If it diverge, then the whole series diverges.
So the integral test still apply. So I modified the integral test a little bit. So what modification did I do? I just add decreasing ultimately, or it is positive ultimately. Okay. So if you want to look at the picture, the relating function is going to be like this. The relating function doesn't have to be positive all the time, doesn't have to be decreasing all the time. What's important here is after some index on, it is going to be positive and decreasing. And then you can apply the integral test. Okay, so maybe we should try some example. Let's try the first example. This series over here converge or diverge? Oh, Diego? Yeah, you want to say converge? Okay, what's the reason?
Is
Okay, Diago, notice that what happened here is exponent on n here is 2, it's greater than 1. That's a very good reasoning. This series here actually behaves very similar to 1 over n squared, the other series, okay? But that will be some other test that we're going to use in the future. But for today, we're going to use the integral test. We're going to look at the relating function, okay? What's the relating function of this series?
We place n here by x, we get
Okay, so 1 over x squared plus 1. So I had to satisfy the 3 hypotheses. What are the 3 hypotheses? Continuous, positive, decreasing. Okay, let's check this off one by one, right? Is it continuous on 1 to infinity? Yeah, there's no discontinuity, right? Yeah, it's okay. Okay, it never be undefined, right? So yeah, okay. Is it positive?
yes.
Yeah, x squared plus 1 is always positive, right? And 1 over that is always positive. Yeah, so we check it off. Okay, so check that off. Is it decreasing? Yeah. Yes. Just briefly give me a reason why. Yeah, when x gets bigger, the denominator gets bigger, right? So it's decreasing, right? Okay, good. So now we can apply the integral test. Let's call it IT. Okay, IT for integral test. So use the integral test, we're going to look for this integral. The integral of this function, x go from 1 to infinity. This is the improper integral of type 1. If we want to do it formally, what do? We place infinity by t, yes. And then let t go to infinity, right? Yeah. So if you want to do it formally, you should do it this way, okay? What's the next thing to do? Anti-duality. What's anti-duality? So it's inverse tangent. We got it. Inverse tangent x. And then you substitute, and then you're going to plug in the replace x here by t, replace x here by 1, right? Okay, let's do that. Okay, so we place what's inverse tangent of t when t go to infinity? It's pi over 2. Okay, it's pi over 2, yes. Okay, and what's pi over 4? Yeah, you got it. Good job. Okay, pi over 4. So the result here equal to pi over 4. Pi over 4. Yes, you got it. Good job. Okay, that's equal to a finite number. Okay, which means that this integral here converge, right? And that equal to a finite number that converge. So if this integral here converge, what can we say about the corresponding series? Also converge, yeah. Remember they count together, right? They converge together, okay? So therefore this corresponding series here converge, okay, by the integral test. So I actually think the way that for me, if I'm looking at this, I think the way that you can see right away is think about this is actually similar to 1 over n squared. Okay, so Diago's way is actually the easiest way to see it converge. However, if you really want to prove it, okay, for today's lesson purpose, we use the integral test. You prove it this way, okay? Okay, good job, you guys. Move on to next one. Okay. Okay, ready or not, here we go. All right, so we look at this series over here. Want to see it converge or diverge? But since today we're doing integral test, let's just use the integral test. Today we're going to try to use the integral test, okay? So for the integral test, we're going to look at the relating function. What's the relating function? Ln x over x. Yes, you got it. Okay. Okay, let's check off the 3 hypotheses. What are the 3 hypotheses? Continuous. Okay. All right. And is it continuous?
Yes.
Yeah, it's undefined when x equal to 0, right? But then we're looking for 1 to infinity. So yeah, so no problem with that. So it's continuous. The second one, positive. Is it positive? It is. It is. Yeah, on 1 to infinity, because Ln of 1 is 0, right? Actually, the first term will be 0. Okay, but then after that, it's all positive, right? But that's okay because we only care about positive eventually, right? Okay, what's the last one? Decreasing. Okay. Is it clear that it's decreasing? Not clear, because what happened to the numerator? When x goes to infinity, and then the denominator also go to infinity, right? So this above here go up, and then down here also go up, right? So you want to see which one go to infinity faster. Use a picture?
Yeah. I mean, because
Oh, yeah.
is obviously like grow faster
Uh-huh.
and
Yeah, it makes sense. Yes, it makes sense. So you can make an observation. Ln graph, how does the Ln graph look like, right? Ln looks like this, right? Ln of x. So it's slowly going up, right? But then y equal to x, y equal to x is going to be like this, like this. So this one
X go to infinity much faster than Ln of x.
this one is this. So eventually, we think that the x is going to win, right? Win over this. Okay. But this stuff here is not obvious. You can, but we do the reasoning. At least you can say some reasoning. You can say x go to infinity much faster than Ln of x, and I will be satisfied if you do it in the exam. Okay. But there's one way to prove it formally is to use. How do you prove a function is decreasing? Show the word t is what? Negative. Yeah, you got it. Good job, you guys. So we can try to show the word t is going to be negative. Okay. So now it's a good time to review taking the word t. What's the word here? This? What kind of rule you use to differentiate this? So it's a quotient rule. So how does the quotient rule here work? The denominator will be what? X squared. Yeah, you got it. Okay. And then the numerator here, differentiate Ln of x, you get 1 over x times x minus Ln x times 1, right? Like this. And simplifying, you got it. Okay. Now, we're trying to show that the derivative here is negative, right? So we try to show that when will this be less than 0? So what is C? Okay. Now look at the denominator here. It is x squared. Okay, and we only consider from 1 to infinity. Remember? Okay. So because the index is going to be start from 1, so on 1 to infinity. So the denominator here is x squared, positive and negative. Always positive on 1 to infinity. So the sign of this is going to depend on the numerator on top, isn't it? Yeah. Okay. So when will the numerator to be less than 0? When will 1 minus Ln of x to be less than 0? Can you solve for x? Okay, let's do it step by step. What's the next step? Let's isolate the Ln of x. Ln of x is what? Greater than 1. Okay. Then x is greater than e. Okay, yeah, you got it. When x is greater than e is negative, right? Okay, so it's like this. Okay, I'm going to draw the picture so that you can see better. Okay, here's the picture. Okay, so what happened here is when x is less than e, that sign here is going to be positive. Okay, and when x is greater than e, the numerator is going to be less than 0, and then divided by this positive quantity, it should be less than 0, so negative.
When the first derivative is positive, the function is increasing. When the first derivative is negative, the function is decreasing. So f here is increasing on the left of e and decreasing on the right of e.
Right. Now the index here starts from 1. So index here starts from 1. So that means now remember the modified version of the integral test. So what do we need? We just need this to be decreasing ultimately. It doesn't have to be all the time, right? So it's like it could be really bad, like you did a lot of wrong things, but at the end you become a bad person, right? So at the end, this is what it matters at the end, right? So it's all forgiven, okay? So over here, then this is decreasing ultimately, then you can actually apply the integral test, right? Then we have to look at the integral, okay? What's the integral? Integral of, what's the function? Integral of ln of x over x, and x go from 1 to infinity, right? We look at this integral. If this integral here converge, then the series converge. If this integral diverge, then the series diverge, right? Okay. So how do you find this integral? Well, it's improper. So the first thing to do is replace this.
Replace infinity by t, and let t go to infinity.
Okay, so that's the formal way to do it. Now, what's the integration technique to do? Okay, let's use that. Okay, good job. Okay, tell your next teacher I'm your teacher. Okay, so it's use up. Okay, so it's use up. Okay, good job. Okay, you let u equal to what?
You want to let u to be a function such that du also appear in the integral.
U equal ln x, and then this part here become du, right? Okay, good. Okay, good job. Now, you're looking at this. Can you tell me what is antiderivative? Okay, what's the antiderivative of u with respect to u? What's antiderivative u with respect to u? U square over 2. Okay, so I'm talking about this, okay? So let me write down. So to get antiderivative of u with respect to u, okay? Like this. And that's equal to what? U square over 2, right? Okay. And what's u over here? Ln x. So it's ln of x squared over 2, right? Okay. So in your mind, you can do all this, right? So think about this as u, and then
you just replace u by ln of x.
Now we're going to substitute the x here by t, and then substitute by 1. And then we're going to let t go to infinity. Okay.
What's ln of 1? ln of 1 is equal to 0.
When t go to infinity, what happens to ln of t? It go to infinity, right? Okay. So when t go to infinity, ln of t also go to infinity. Remember the graph for ln, right? It goes slowly, slowly up and up and up, right? Okay, so that also go to infinity. So this whole thing, so what about this limit? What's the limit of this? Infinity, you got it, good job, okay? So that's infinity, so which is divergence, right? So it's divergent. So we found that this integral here diverge, okay? So what can we conclude about the relating series? Converge or diverge? It diverge because they die together, right? So it's going to diverge by the integral test. So now you get a taste of how to use the integral test to prove something like this. Here's a couple notes.
Here is a final remark.
It is important to know before leaving this section that in order to use the integral test, the series must eventually be decreasing and positive. If they are not, then the test doesn't work. And also remember that the test only determines the convergence of the series, but does not give you the result. Okay, does not give you what does it convert to. It just say it converge, but it doesn't tell you what does it convert to. Now let's take a 10-minute break and then we finish the second part of the section.